Good evening, students. Am I audible to you all?
Yes, sir.
Thank you. On behalf of IGNO Regional Center Bhubaneswar, I welcome you all to this online platform relating to your theory classes of postgraduate diploma in analytical chemistry program. Yesterday, we have started the second paper, subject paper of your that is MCH-002. Yesterday, we have completed 2 units, and in that units we have discussed the things related to your separation techniques. Physical chemical techniques are there. In physical separation technique we have discussed some method of your magnetism method, then filtration, distillation. Then chemical process we have discussed chromatography and ion exchange. It is followed by electromigration, etc. And in the second block, that is the latter part, we have discussed some statistical analysis related to your distribution in organic and aqueous phase, the distribution coefficient, distribution ratio, separation factors, and various examples involved in that. So these 2 units we have covered up, unit 1 and unit 2. Today we will resume the session with the next unit in your block 1, that is unit 3, which is related to again to your solvent extraction process. So now I am sharing my screen with you. We will discuss in by using the PDF provided by IGNO. I think my screen is very much shared. Is it visible to you all, students?
Visible, visible.
Okay. So in the first part, unit 2, we have discussed solvent extraction 1 and part 1. This is unit 3 belongs to your solvent extraction part 2. So in this unit, we have some objectives and extraction equilibria, which involve extraction of metal chelates by solvation, by ion pair formation, then that is synergism. Then the factors involving the extraction, the factors are like your pH factor, molarity of the acid, metal ion concentration, presence of salting out of agents, presence of masking agents, concentration of the extract, nature of diluent, different approaches of the separation of metal ion, that is stripping, pH of the aqueous phase, acid molarity, presence of masking agent, selective stripping. Then at the end we have some criteria for choice of organic phases, and then we have the summary part. Let's have the discussion with some introduction. That is, as we know, this separation technique is a different branch of science known as separation science, which is very much helpful to separate the different components in a mixture. A mixture is mainly composed of minimum 2 components, and by separating the components in purest form, we can use it in different chemical analysis or in other applications related to different branches of science, that is biochemistry, biotechnology, in basic sciences also. So the objective of this unit to explain the extraction of metal ions with some important class of extracts, that is some foreign chemicals we may use as extract, which is useful to form different compounds or complexes with the component which we are desired to separate. Then enumerate different aqueous and organic phases parameters which affect the extraction of metal ions. Then there is distribution of the component in two phases, that is aqueous and organic phase. This is related to your chromatography. Describe various approaches which generally adopted for metal ion separation. So different approaches are there. Decide the criteria for the selection of the organic phase, particularly for commercial applications. So these are the four objectives of this unit. Then studies on extraction equilibria. So the equilibria means it is the balancing of the chemical reaction, that is equilibrium. So where the rate of forward reaction is same as rate of backward reaction. The equilibrium is seems to be a static one, but it is not static, it is always dynamic. That is, the rate of forward reaction is equal to rate of backward reaction. So in this equilibrium process, we are having some slope analysis. That is, we have the equation of a straight line, that is y equal to mx plus c, where m is the slope and x plus c is the y equal to mx plus c is there, and we have some spectroscopic analysis related to IR, UV and visible. Then in this section we have some extraction processes involving equilibria, that is extraction of metal chelates we have discussed yesterday. That is, metal chelates means it will have some chelating agents or chelating ligands, like your ethylene diamine or ethylene diamine tetraacetate ion, EDT ion. So by these chelating ligands, we we have um, we have changed the component to a new complex form, that is the metal chelates. Then by extraction by solvation process, by selecting a suitable solvent, we may extract the component. Then again, extraction by ion pair formation, that means it is a ionic ionic component which is separated from the mixture by ion pair formation method. Then one another is there, that is due to synergism. Synergism is nothing but your supporting agent for separation of the component from a mixture. So let's have the first one, that is extraction of metal chelates. So in this extraction system, there is formation of compound or complex compounds are there. That means here some chelating ligands are reacted with the component to form a compound, and in the latter part that compound is separated and we get the component in the purest form. Metal chelates represent a type of coordination compound in which the metal ion combined with a polyfunctional base capable of occupying two or more positions of the coordination sphere of the metal ion to form a cyclic compound. So the word chelate, this is a Latin word, and the word chelate means it is, in English it is cycle. So this chelating agent or chelating ligands formed a cyclic compound with the component or the metal ion which we are desired to separate. So some chelating agents generally used for separation of different components in a mixture are: number one is oxime. This oxime is nothing but 8-hydroxyquinoline. This is the structure of 8-hydroxyquinoline or oxime. This structure is just a combination of a phenol with pyridine. So if I condensed the two rings of phenol and pyridine, then the oxime compound is formed. So this is your phenol, that is benzene ring with OH, and this is pyridine, that is benzene ring contain one nitrogen instead of carbon. So this is known as your oxime. So the metal ion is forming compound or complex compound with oxygen. The reaction will be the metal ion Mn plus reacts with NHOX. That means here this ring and this OH, here it is written as OH, that this is the oxygen part. So metal ion reacts with oxygen to form MOXN plus plus removal of H plus ion. So similarly, the second reagent, that is chelating agent for removal of the component, that is metallic component, is your dithiazine. Dithiazine, the structure is this one, which is also is diphenyl thiocarbazone, popularly known as dithiazine. So dithiazone is also known as diphenyl thiocarbazone. The structure is just like this. Here, where the word thio is there, just remember sulfur is present. If thio is there, that means sulfur is present. If azo is there, then nitrogen is present. Okay, so if oxo is there, oxygen is present. Just like this, you have to remember that what atom is present in that compound. So thio means it is sulfur. Then the compound is just like this: sulfur double bond with carbon. Then NH, two numbers of NH are there. Then followed by one phenyl ring. Then here N double bond N is there. Then one phenyl ring. So this is your dithiazone. So by using either oxygen or dithiazone, we are able to form chelating complex, which is a very effective one for the separation of the component in a mixture. So this dithiazone is insoluble in water. This is very important. This is insoluble in water because dithiazone is an organic compound, and generally organic compounds are non-polar in nature, and water is polar in nature, as the general rule said that likes dissolve likes. So polar dissolves polar and non-polar dissolves non-polar. So that's why this organic compound is insoluble in water, but it is soluble in carbon tetrachloride and chloroform, because the carbon tetrachloride and chloroform, these are organic solvents, and this is also organic one. So that's why dithiazone dissolve in carbon tetrachloride or chloroform. And the metals which are very much forming chelates with dithiazone includes manganese, iron, cobalt, nickel, copper, zinc, silver, cadmium, tin, and lead. So these metals can easily form complex with dithiazone for their separation. If I go for physical chemistry, then some equilibrium equations will be there, and here just we will see the derivation, that is metal. Let us consider a metal ion with charge N with extracting chelating reagent to form metal chelate. When the aqueous phase containing the ligand HR, this is the ligand HR, is brought in contact with organic phase, the reagent distribute itself in both the phases as the equilibrium attains. That is the ligand in aqueous phase, that is HRA, will be equilibrium with ligand in organic phase, HRO. Then here the distribution coefficient will be HRO concentration divided by HRA concentration. Always remember, the distribution coefficient or the equilibrium constant is concentration of the product divided by concentration of the reactant. So in this equilibrium, concentration of the product will be HRO, that is ligand concentration in organic phase divided by ligand concentration in aqueous phase. So these things are there. So again, so this is the distribution of the ligand in aqueous and organic phase in the equilibrium. Then this is the distribution coefficient. Then in the aqueous phase, what happened? This ligand HRA will dissociate to give H plus and R minus. This is in the aqueous phase. This is in the total reaction, that is in equilibrium. So we will discuss one by one what will happen in aqueous phase and what will happen in an or in the organic phase. So in aqueous phase, what happen? This ligand in aqueous phase will dissociate to give H plus and R minus. Then the equilibrium constant again, or the dissociation constant Ka, it will be concentration of H plus, concentration of R minus divided by concentration of Hr. So these two equations are very much understood. Then the chelating anion R minus react with Mn plus to form chelate as shown below. So now what happened? This negative ion R minus will form chelate with the metal ion, which is our main component to be separated. So this R minus, which we have from the aqueous phase dissociation, will react with Mn plus, that is a metal ion, to form the chelate. So now this metal ion reacts with the negative part to give the chelating compound or the cyclic compound MRN. So here the constant becomes Kf, that is formation constant, because this is our main product or the primary product which is formed in this step. So this is Kf. So Kf will be Mr concentration in aqueous phase divided by Mn plus concentration in aqueous phase plus R minus concentration in aqueous phase to the power n, because in equilibrium equation or from law of mass action, we understood that the coefficient becomes to the power. Here the n is the coefficient of the R, and in equilibrium equation or the distribution equation, this coefficient becomes the power here. That means nr becomes rn. Okay, so this coefficient is nothing but your number of moles. So if it is 2r, then it is r minus to the power 2, that is square. So this type the equation is written. Then the concentration of the complex form, that is the cyclic complex, that is chelating complex form in aqueous phase, it is equilibrium with complex in organic phase. Then finally the distribution constant of the complex, that is kdx, it will be concentration of complex in organic phase divided by concentration of the complex in aqueous phase. This is very much clear. So in this derivation, we are able to find out the distribution coefficient of the distribution constant of the complex by using the chelate formation method. That is the formation of the cyclic compound from the by using the metal ion and the chelating ligand. So first, the ligand is in equilibrium, organic and aqueous. Then this is the distribution coefficient, and this is the dissociation of the ligand in aqueous phase. So after dissociation, the negative part of the ligand reacts with positive metal ion to form the metal complex, and this metal complex will have the formation constant like this, that is Mr in aqueous phase divided by Mn plus A, R minus concentration A to the power n. Then these this complex will be distributed uh, in organic and aqueous phase and are in equilibrium, and this is the final distribution constant. Someone is unmuted, I think. Ansul, you are please mute yourself. Ansul. So this is the final distribution constant equation for the complex form by using chelating reagent to separate the component in a mixture. So this is solvent extraction part 2 section we have studied. So we assume that the metal ion in the aqueous phase predominantly exists as Mn plus only, and in organic phase it is Mrn. That is, in organic phase the metal ion is converted to the metal complex with the chelating ligand. So the assumptions are the metal ion forms no hydrolysis or anion complex in appreciable amount. So these are the assumptions. The chelate concentration in the aqueous phase is negligible. The concentration of the intermediate chelate species is negligible. So these are the assumptions, and by using these assumptions, we are finally find out the distribution constant of the complex form, that is Kdx equal to Mrn organic phase divided by Mrn in aqueous phase. So if these assumptions are taken as valid, then the distribution coefficient D equal to concentration of metal ion in organic phase divided by concentration of metal ion in aqueous phase. So what is the concentration of M in aqueous or organic phase? It will be the complex, that is Mr, and in aqueous phase it is the ion, metallic ion. So this is the distribution now. Mrn, this is the complex formed in organic phase, divided by the metal ion concentration in aqueous phase. So if I equate the equation 3.1 through 3.8, the final 3.9 becomes this one. So by using 3.1, the previous equation, this is 3.1, this one, and this is 3.8 and 3.8 this one, and 3.9 this one. Then the final, by equating these two, these three, we will have the final equation, that is D equal to K of formation Ka to the power n K dx divided by K n dr Hr organic phase divided by S plus aqueous phase. So this equation has been experimentally verified for various metal chelates, and it is evident that D, that is distribution coefficient, is directly proportional to these constants, that is formation constant, that is aqueous phase, and this is the distribution coefficient, and this is the distribution coefficient of the ligand. And also it is also inversely proportional to, that is KDR, and also inversely proportional to formation of H plus ion, that is the protons. So if we interpret this result in order to have greater extraction, Kf should be as large as possible, because when the value of Kf is high or large, then more and more product will be formed, and the complex formation will be faster, and we can easily separate the component from the mixture. So the factor is very much important, that is Kf, that is formation constant. This must be has high value. If the value is high, then formation will be better, that is the reaction is a move more towards product side if Kf is more. That is distribution coefficient is directly proportional to the constant or dissociation constant and in aqueous phase, because in aqueous phase if the dissociation constant is more, then R minus will be formed faster. If the formation, this one, if the R minus is formed faster, this one, then the formation of the metal complex will be faster. So if the metal ion complex will be faster, then the separation will be easier. Then since D proportional to K dx, it will remain, it will mean that the complex should have maximum concentration in the organic phase. So this is the distribution of the coefficient in organic phase. The next will be, it is D proportional to HR, this is the ligand in organic phase. So if the ligand concentration in organic phase, formation of the complex will be easier, and there will be easy separation. Then the last one is your inversely proportional to S plus ion concentration. If the S plus ion concentration is less and less, the distribution will be more and more, right? Then at last, it may be important to consider the role of H plus or pH. That is, if the H plus ion concentration will be less and less, then the pH will have the pH will be more, that is high value. If it is more acidic, then the negative ion formation will be easier and the complex formation will be easier. So finally the distribution constant D will pull this factor into, that is ligand concentration in organic phase divided by H plus N concentration in aqueous phase. Then if we go for this constant as K star, then finally this the equation 3.10 will become constant K star multiplied by your ligand in organic phase divided by concentration of H plus in aqueous phase. And if I multiply log in both the sides, then I will have log D equals to log K star plus n log HR in organic phase minus n log H plus N concentration in aqueous phase. So if I multiply log, then by this is your log D equal to log K star plus n log, this is your log HR organic phase plus this is minus log H plus is nothing but your pH. So this is the mathematical form of your pH, the pH equal to minus log H plus N. So this is changes to your plus N pH, because minus log H plus is pH, so minus become plus here. So this is the equation. And if I if I plot, that is y equal to mx plus c, then log D will be your y and pH will be your x-axis and n, that is slope, will be your n, this one n. Okay, and this will be your intercept. So similarly, this equation is there from 3.13. Again the reagent is, if the reagent is constant, that is the reagent concentration is constant, then this constant into constant, this becomes another constant, and the H plus N concentration will be varied. Then the assuming V and V0 to be equal, that is volume in aqueous phase and volume in organic phase to be equal, then the this is your percentage distribution coefficient. This will be from unit 2 we have already studied yesterday, that is 100D divided by D plus 1, and by simplifying these things we will have D equal to K star dash 1 by H plus concentration, or if I equating these two, we will have E by 100 minus E. So this will be our final equation with respect to the H plus N and the percentage of the distribution coefficient. Then after formation of chelating complex, we have the second one, that is extraction by solvation method. So extraction by solvation means we will have some different type of extracts which are used for the separation of the component from a particular mixture. So it has been pointed out that large number of solvent extraction systems are based on the solvation of neutral inorganic molecule or complexes by electron donor containing extract. This is very important, that is electron donor. That is these are very much your electron rich species. It may be nucleophile or it may be a basic one. The basic role of the solvating molecule is to increase the solubility in the organic species. This is very much important. So the extracting species is more hydrophobic. That is, hydrophobic means it hate uh, mm, it has the headness towards water. Okay, and it promoting its transfer to organic phase. This is the condition is there, that is hydrophobic, and it has more prone towards the organic phase. And we have two distinct type of solvating extracts. Number one is the extract which are bonded to oxygen with carbon, that involves the functional groups like ether, alcohol and ketones. And if some sulfur and phosphorus are there, Then functional groups like alkyl phosphates or alkyl thiophates are generally used. So these are some examples that just read out these things, and we have some examples here. That is formation of FeCl4 minus anion in the aqueous phase. That is your FeCl4 minus in aqueous phase. So if I go for hexa aqua iron 3 plus complex ion, reacts with the chloride ion Cl minus 1 minus Cl minus, then the equilibrium constant K1, then one water will be displaces by one Cl minus ion, then the new compound or the complex ion formed is FeCO5 Cl2 plus. This 3 plus becomes 2 plus because chlorine minus 1 will be neutralized one positive charge. Then one water molecule is separated. Then this complex ion will react with another chloride ion to form FeH2O4 Cl2 plus. This 2 plus becomes 1 plus. Then again one water is removed. Then in the third step, another chloride is added and we will have one neutral complex, that is FeH2O3 Cl3 plus another water is left out. Then in the last step, we will have FeH2O whole 3 Cl3 plus Cl minus. We have FeH2O2 Cl4 minus plus H2O. So at the end, we will have the net reaction or the overall reaction will be, that is FeH2O whole 6 3 plus. This is our first reactant. Will react with stepwise 4 chlorides. We will have stepwise 4 equilibrium constants, and we will have the product as FeH2O2 Cl4 minus plus 4 water. So the final equilibrium will be, that is K dash equal to K1, K2, K3, K4, which is equal to FeH2O whole twice Cl4 minus concentration into H2O concentration to the power 4 becomes, because here the coefficient become the power to the power, divided by FeH2O whole 6 3 plus plus Cl minus to the power 4. So this is the overall final equilibrium constant for this extraction. Then formation of the solvate. The next step is to formation of the solvate, that is extracting in the organic phase. So high acidity, water activity decreases and the ether activity in the aqueous phase increases, because this solvation process is more hydrophobic, that is it is less prone towards aqueous phase, and it is more prone towards the organic phase. So that's why the formation of the solvate involve the less reactivity of towards water and more activity towards the organic phase. So the complex formed in the first step, this is the step 1, formation of this FeCl4 minus. So this will be react with one ether, that is R2O, which will form a complex like this, that is FeR2O twice Cl4 minus plus 2 water. Then again the reaction will be, the hydronium ion will react with ether to form R2OH plus plus water. Formation of the extractable complex. Then this complex, this one will be react with R2OH plus, this part, and this will give this complex. And another complex is there, that is hydronium ion reacts with the first step. The complex is formed in the first step, that is FeH2O2 Cl4 minus. This will form this complex, hydronium Fe water twice Cl4 minus. Then at the end we have some HS plus, that is thio related ligand, reacts with the thio complex to give this one. Then distribution of the reagent and the complex. This is the reagent we have the distribution coefficient in organic phase as well as in aqueous phase. So as the solvation in solvations process, organic phase is more important because organic compounds are formed. So that's why we have the organic phases only here. That is, in the first case, we will have Kd in organic phase, that aqueous changes to organic, and also in the second, aqueous is also in equilibrium with the organic phase. Then the polymerization of ion in the ether phase. This is this compound or organic phase will change to HS plus FeH2Cl4 minus in organic phase. That means the a small molecule becomes a bigger molecule, like the pure polymer. That is, n number of ethylene gives polythene. In that sense, n number of this complex n number of this complex will form a bigger molecule, that is this one. Just wait. Hello. Oh, sorry for the inconvenience. So we have in the next step, that is your in step 5, we have some polymerization process where some units which are varies from 2 to 4 of the this complex in organic phase will be converted to one bigger molecule, that is in one unit, that is bigger molecule. And the next step is your dissociation of the ion pair and the reagent in the organic phase. This is the reaction, that is this complex will have the dissociation, that is ionization, that is HS plus will be separated and this part will be separated. That is, both are in organic phase. Okay. So in solvation, we only consider the organic part, organic phase distribution. And in the sixth step, we'll have the dissociation step, that is the complex ion is dissociated to two ions. And also we have another dissociation, that is HS plus Cl minus will dissociate to give HS plus Cl minus. Then now considering the overall distribution of the iron in different forms between organic and aqueous phase, then in general this will be distribution equal to iron concentration in organic phase divided by iron concentration in aqueous phase. Then what are the ions or complex ions present in organic phase? Now this is in organic phase, this the plus the second one, this is organic phase, the third one, this is also an organic phase, and in aqueous phase these two terms are there. So if I go for the equilibrium constants, then D will be the summation of these overall summation of these constants. So the following inferences can be drawn, that is, in a relatively high iron concentration where polymerization takes place to a significant extent and dissociation relatively unimportant. If the higher concentration of iron is high, then polymerization will be significant. That is step 5. And when the region of low iron concentration, the dissociation of the complex is only significant, because in low iron concentration there will be no polymerization will occur, and the respective constants will be omitted. Then we'll have the last conclusion. It is clear that the extraction of iron 3 is favored by increasing acidity, because as the H plus ion is present in it is inversely proportional to the distribution constant. So that's why by increasing the acidity, the pH will increase, and the H plus ion will concentration will decrease, and the formation or the distribution constant will increase. So these three things you have to remember, that is concentration of the iron, if the concentration is high, if the concentration is low, and the effect of pH in the extraction of Fe3 plus ion, that is increasing acidity. Then the third part is ion pair formation, and this ion pair formation um, is by extraction of permanganate ion by tetraphenyl arsonium chloride. You have to remember these compounds under this category. And extraction of anionic metal complexes by high molecular weight amines, popularly known as liquid anion exchanger. So this liquid anion exchanger, this is nothing but your amines, right? So there are two types of extraction processes are there, that is in under our category ion pair formation. This is your permanganate ion by tetraphenyl arsonium chloride and high molecular weight amines, that is also known as liquid anion exchanger. Then extraction of tetraphenyl arsonium permanganate, this one tetraphenyl arsonium permanganate. So it is water soluble because this is ionic in nature. This forms chloroform extractable complex with anion like permanganate. This is perhenate and pertecnate. The quantitative treatment to the equilibrium is just as proposed. That is dissociation of the reagent. That is tetraalkyl. If R is phenyl, then it will be tetraphenyl arsonium chloride, and R is phenyl here. So tetraphenyl arsonium chloride in aqueous phase, it will be dissociated because this is an ionic compound. So this will dissociate to give chloride ion plus tetraphenyl arsonium ion. Then the equilibrium constant will be concentration of both the ions in product side divided by concentration of the reactant. This will be the equilibrium constant, the dissociation constant. Then formation of the association complex, then complex will be formed with the permanganate ion. Permanganate will be MnO4 minus, this one. So here the positive ion R4As plus in aqueous phase will react with permanganate ion to give the complex, the manganate complex, permanganate complex. The formation constant will be the concentration of this complex in aqueous phase divided by the concentration of tetraphenyl arsonium ion in aqueous phase plus permanganate ion in aqueous phase. This will be the formation constant. And also the value of Kf is very small here because the concentration of the product is very less in this reaction. That's why. Distribution of the reagent and the complex. How the reagent and complex is distributed. Then the distribution there will be equilibrium of the complex, that is tetraphenyl arsonium chloride in organic phase is in equilibrium with tetraphenyl arsonium chloride in aqueous phase. Then the distribution coefficient will be concentration of this complex in organic phase divided by concentration of the complex in aqueous phase. Then this is the reagent. What will be the complex? The complex will be with permanganate ion. So R4As plus manganate ion divided by R4As manganate ion. So this will be the concentration equation for your distribution of the complex. Distribution of the complex equation, this one. Then dimerization is another part of this separation, that is dimerization of the reagent and the complex in the organic phase. Then this reagent will be dimerized to give a bigger molecule, like polymerization. Okay, so there are two molecules of these combine to give one molecule. So now the uh, the dissociation constant or the equilibrium constant Kp, that is equal to the organic phase concentration divided by the reactant concentration organic phase square to the power 2. And this R4As manganate ion, this is the ligand, and or this is the reagent, and this is the complex. Okay, so now for the complex, what happened? The Kp dash will be the concentration of this ion in organic phase divided by concentration of the reactant to the power 2 in organic phase. So the first one is for your reagent and the second one is for your complex. If the distribution of the permanganate in the two phases will be the permanganate distribution in organic phase divided by permanganate distribution in aqueous phase. So what is permanganate distribution in organic phase? We have the complexes or complex ions like this, that is R4, that is tetraphenyl arsonium permanganate concentration in organic phase, and also tetraphenyl arsonium manganate twice in organic phase. So this is the dimerization. Then we'll have in aqueous phase we have permanganate ion plus this one. So this will be the, if the permanganate concentration is low, the dimer formation may be neglected. Then the reaction this equation will become this one. Okay, so this means that the distribution ratio of the permanganate complex is solely a function of the equilibrium concentration. We know that the chloride ion concentration tends to reduce the concentration of tetraphenyl arsonium cation, thus they are reducing the extraction of the complex. So this will have your solvation process. Then we have after permanganate distribution, we have high molecular weight amines will be there. Amines mainly we have the quaternary amine, quaternary ammonium salt. So this is first one is your this include your primary, secondary, tertiary, as well as quaternary ammonium salts. 4 variety of salts are there in amine group, and we will take the tertiary one. This is R3NO hydrochloric acid. This will have R3NH4 NH plus Cl minus. And if I go for an anion, then the chloride will be exchanged and we will have this one. Then the complexes formed Examples are FeCl4 minus, CdCl4 2 minus, ZnCl4 2 minus. These are the examples involved in this amine part. Then these are some chemical reactions. Just like the above reactions, you just follow these things. Then we will have the slope, that is amine versus log D. We have the slope like a straight line, and after this we have extraction by synergism method. The synergism literally means working together. This is very important, working together. And this concept was first cited in the research paper given by Blake and others in 1958. They observed that when a dialkyl hydrogen phosphate, that is RO2POOH, used in conjunction with certain organophosphorus solvating molecule like like tributyl phosphate TBP, the extracting power of the mixture exceeds the sum of the extracting power of the individual extracting reagent. That means when some extracting mixture is added to an individual component, then the extracting power of the mixture exceeds. So this phenomenon was first observed by Blake, and the different type of extracts used for this mechanism are HTTA, that is thionyl trifluoroacetone, and your TBP, that is tri-N-butyl phosphate. So this is the reaction. So when metal ion reacts with either of these two reagents to give a complex ion plus removal of H plus ion. And similarly, the second one, that is tributyl phosphate one, the same thing will happen, and this one will be the MAN inorganic phase reacts with TBP to give this complex. So here HCTA has been used with different solvating molecule like TBP, TOPO. These things are there. TPP, triphenyl phosphate, and these are the increase in basicity of the ester. One of the extract, a ligand or an acid, neutralizes the charge on the metal ion preferably by forming a chelate. The same mechanism is here, that is formation of the chelate, which we have discussed in our part 1. The list of the ligand is very large. The acid can be organophosphorus or carboxylic acid. The solvating reagent should displace residual coordinate water from the neutral complex. The maximum coordination number of the metal and the geometry of the ligand should be favorable. So this is one another important criteria for the complexing or complexation of the component to the extract or the chelating reagents. A little more complexity in the formation of synergistic adduct is being presented by taking the extraction equilibria of zinc, cadmium in the chloroform solution of propionic, butyric or valeric acid in presence of amine. So this synergistic effect is related to your back bonding. So when a ligand donates its pair donates its lone pair to the vacant orbital of the metal, then the metal also back donated the electron to the metal ligand, and this is known as synergistic effect. So this synergistic effect is also seen in this mechanism. Then we have some equations here with our aliphatic monocarboxylic acid and that of the amine, and we will have some equilibrium constant equations and just go through these things. Just remember, when we write the equilibrium constant equation, always write the product concentration in the numerator and the reactant concentration in the denominator. Just remember this thing, okay? Then after this part we have the last one. What are the factors influencing the solvent extraction process? The first one is pH. As we know, pH is negative logarithm of H plus ion, or it is the full form of pH will be the prudency of hydronium ion. We generally used the term H plus ion, but it is more correct to use H3O plus, that is hydronium ion, in place of H plus ion, because the H plus ion is always associated with the aqueous solution to give hydronium ion. So where the H plus ion concentration is more, the pH will be less, because it is negative logarithm, and where the H plus ion concentration is more, then pH will be less, and vice versa. Okay, so equilibrium pH with percentage of E, that is qualitative extraction curve. This is for different ions. This is I think this is brought from different research papers, so we need not have some discussion on this part. So these are some extraction of some metals with Versatic 9, and we will have another reagent, that is DEHPA. The full form are here, just read out these things. And this is in terms of percentage, that is your separation factor in percentage. So this is another expression. Then you all are knowing that what is molarity of the acid. Molarity means, it is in general term, it is molarity refers to your number of moles present per liter of the solution. So if the solution is an acid solution, that is molarity of the acid. So depending upon different concentration, that is molarity of the acid, different metal ions can be separated from the mixture. So there will be ion pair formation in presence of that is low pH. Okay. So just read out what is the pH condition for which metal ion, and these graphs will be there. Concentration of HCl in moles per liter, that is molarity with respect to percentage of E. Then we have the same one in this part also. This is different types of your amino acids, that is alamine, then alamine 336, alamine 336, amberlite, tribenzyl amine. So these compounds are very much researched, and the data are given here. So you need not wish to remember all these things. Okay. So effect of metal ion concentration, that is if the metal ion concentration is more, then there will be high percentage of reaction with the extract or the chelating ligands, which will helpful to extract the metal. So it has been emphasized in the beginning that there is no effect of the metal ion concentration on the distribution ratio. This will mean that both the tracer and the macro amount of the metal may be expected to extracted to the same extent under similar equilibrium condition, provided the solubility of the extracting species in the organic phase is not exceed. The relation is between M in aqueous phase divided by M in organic phase, and the plot known as loading curve or extraction isotherm. Isotherm means it is at constant temperature. Iso means constant, and therm means temperature, or this is known as at constant temperature. This plot is plotted. And presence of salting out agent. Salting out of agent means it is just the phenomenon like your salting out of salt, that we we have collected, or that is salt from salty water of sea or ocean. How we added some solid salts, that is to the salt water, and after some time or some days we see that salts from the salty water comes out. This process is known as salting out of salt, and this is an application of your common ion effect, which you have already studied. That is due to presence of the common ion, the equilibrium gets reversed, and solid sodium chloride salts are solid sodium chloride salts are prepared. So this is just same as your salting out of salt type. That is common ion effect application. Then presence of masking agent, we the masking agents is just like your EDTA, also your masking agent, EDTA, or tartarate, cyanide, citrate, fluoride. These are all your masking agent which will mask the component which we wish to separate from the mixture. So this will mask the component and this will help us to separate the component from the mixture. Then we have some extract. The same thing is here again, that with increase in extract, with increase in extract concentration, the distribution coefficient will be more, and we will easily separate the component from the mixture. This is extract type. So some examples are here, just read out these things. And we have some plots, that is log of alanine, that is one amino acid, with log D. We'll have some with some concentration of the acid, how the log D will vary. This is also another one is there, that is cyanics, another compound. And nature of the diluent is also an important one. The role of the diluent on the ex- extractability of the extract has been discussed in detail in section 2.4. So yesterday we have studied. It has become quite apparent that the diluent are not as inert as they might appear to be. The mechanism of their role is quite complex. In some instances, a decrease in the extraction of metal with the polar nature of the diluent has been reported, but from the data available in the different system, it is difficult to ascribe a single property of the diluent to change in stability. So this is already studied. So different approaches for metal and separation. Number one is stripping. This is removal of the extracted solute from the organic phase for further processing. This is removal of the extract, that is the solute, from the organic phase. This is reverse of extraction. That is, this is not from the aqueous phase. This is reverse. That is reverse. That is extraction from the organic phase. Then we have some masking agents we may use, that is EDTA, tartarate, citrate, and the factors like your pH, acid molarity, presence of masking agent, selective stripping of the organic phase. These factors will affect the removal or separation of the metal ion from a mixture. This is the pH equations are there, and also we have in this unit this much. I think acid molarity in aqueous phase already discussed these things. So just read out for which metal at which oxidation state, what is the molarity of the acid is used. Just try to remember 4 to 5 meters, nothing more than that. And we have some examples here. What is the metal type, what is the ratio, what concentration of hydrochloric acid is used, what is the cyanics 923 at molarity, then metal ion, what is remaining, what is recovered, everything is there. This is all, these all are the research datas. Okay, so you need not have to remember all these things, just try to read out these things. These are all are same. These are some amine diluent separation factor, beta is also there, and presence of masking agent, the same thing. Selective stripping is there. Then at the end we have the chapter, that is unit 3 is completed. And let's have some 5-minute break. Then after that we will discuss, just wait, we'll discuss unit 4. What is this? I think this is all about chromatography. Yes, this is chromatography. So for chromatography, I have, I think, one, I have prepared one PPT for you. So let's have a 5 minute break, guys. Some refreshment you take, and after 5 minutes, we will again meet. Thank you. Am I audible, students?
Yes.
Okay. So in the next unit, that unit 4, we have general principles of chromatography. As discussed yesterday, the chromatography technique is widely used for separation of different components in a mixture. So based on the different phases used in chromatography, the chromatography is of various types. So what are the different phases used? It generally has two phases, that is stationary phase and mobile phase. The stationary phase may be solid, it may be liquid, and the mobile phase may be liquid or gas. So depending on the type of stationary phase, type of liquid phase, or the type of mechanism used, chromatography is of various types. So the chromatography, the general principle of chromatography involve the important factor which is known as retention factor. This is very important, retention factor. In short, it is written as capital R small f, retention factor. So this retention factor is important for to estimate or to determine the different components present in a mixture. So depending on the stationary phase and the liquid phase, various chromatography are liquid chromatography, gas chromatography, supercritical fluid chromatography. This is not widely used and this is not also very much user friendly, so this is not discussed here. Only liquid chromatography, gas chromatography, paper chromatography, thin layer chromatography, high performance liquid chromatography, and another is the GCMS, that is gas chromatography, mass spectroscopy. These things are discussed in remaining units of your this paper MCH-002, and today we will discuss the general principle of the chromatography. So before going through the details in the PDF, let's have some basic knowledge on chromatography in this PowerPoint presentation. So I'm not going through these things because these are the historical things are there. So uh, Mikhail Sweat, in a Russian botanist, who first discovered the chromatography method, and he is from 1870 to 1919, and in 1906 he was discovered the mechanism of chromatography. Later it was advanced by your two scientists, Martin and sorry and other, who awarded the Nobel Prize in 1952, I think. He called the new technique chromatography because the result of the analysis were written in color along the length of the adsorbent column. As chrome means it is color. Okay. So as the result are produced in different colors, so that's why Sweat named this mechanism as chromatography. So chrome means color and graphene means to write. So that, so this is the meaning of your chromatography, that is color write. That means the results are written by colors. So thin, this is an example of thin layer chromatography, which is used to separate colorful components in the plant extract, seen by Mikhail Sweat. These are again some histories. Okay. The chromatography has application in every branch of physical and biological processes. So 12 Nobel Prizes were awarded between 1937 to 1972 alone for working in which chromatography played a vital role. So all the research activities in science will fruitful when your raw material is in the purest form. So how can we get the raw material in purest form? By separating the component from their mixtures, and to separate that component, chromatography plays an important role for separation. So the substances in a mixture are not chemically combined, so they can be separated through some physical methods. So chromatography is a technique for separating the components, generally solutes, of a mixture on the basis of relative amounts of each solute distributed between a moving fluid stem called the mobile phase and a continuous, that is a stationary phase, which is constant. So there are two phases, mobile phase and stationary phase. The mobile phase may be either a liquid, sorry, the mobile phase may be either a liquid or gas, and the stationary phase may be either solid or liquid. So stationary phase cannot be gas, and mobile phase cannot be solid. Just remember these two things. Which the phase which is mobile cannot be a solid one, and the phase which is stationary cannot be a gas one, gaseous one. So chromatography is the ability to separate molecules using partitioning characteristics of a molecule to remain in a stationary phase versus a mobile phase. Once a molecule is separated from the mixture, it can be isolated and quantified. So the mechanism is partitioning characteristics, how it is partitioned in two different phases, that is mobile phase and a stationary phase. And after the isolation, it can be easily quantified. So different chromatographic techniques. So under this, we have, depending on the stationary phase and solid phase, sorry, stationary phase and mobile phase, the different chromatography techniques are. Under stationary phase, if it is thin layer chromatography, paper chromatography, and column chromatography. Under mobile phase, we have liquid chromatography and gaseous chromatography. So this is TLC, PC and CC. This is LC and GC. So this is depending upon different types of stationary and mobile phases. And depending upon the type of force of separation, we have adsorption chromatography, where the different components gets adsorbed on the solid phase. Partition chromatography, there will be partition distribution of the component in mobile and stationary phase. Ionescence chromatography in both the phases. Gel filtration will be there, and affinity chromatography will be there. So these 5 types of chromatography is based on the force of separation of a component from their mixture. And also on the basis of this thin layer chromatography and paper chromatography, these two are two-dimensional chromatography, and color chromatography is three-dimensional column chromatography. This is a cylindrical tube is there, where silica gel of different pore size is used for the separation of different components. So these two are two-dimensional, and this is three-dimensional. Thin layer chromatography, paper is used made up of silica gel or alumina. Then where the mixture is tested. For paper chromatography, chromatography paper is used, and the same method is applied. Here it is written thin layer chromatography. It is a method for identifying substances and testing the purity of the compound. TLC is a useful technique because it is relatively quick and requires small quantity of the material. Separation in TLC, thin layer chromatography, involve distributing a mixture of two or more substances between a stationary and a mobile phase. The stationary phase is the thin layer adsorbent, usually silica gel or alumina coated on a plate. The mobile phase is a developing liquid which travels up the stationary phase, carrying the sample within it. The components of the sample will separate on the stationary phase according to how much they adsorb on the stationary phase versus how much they dissolve in the mobile phase. So this is just an example of your TLC, thin layer chromatography. Just see here, this is a thin layer chromatography paper, also known as plate, and this is known as, this bottle is known as chromatogram or chromatography chamber. And here what happened? First of all, they are, so first of all, one line is written here at the bottom, then some the mixture to be separated is added here by using a thin capillary. So after this, in 10% hexane or 20% or 5% hexane solution, this paper is dipped inside this bottle known as chromatogram, and after some time we will see different components are moving upward with different distances. So the different parts of this chromatography are, this is the cover, this one black one, this is glass tank, that means this is the bottle, TSC plate, that means this is the paper, this is sorbent, that is the upper coating layer of this paper, this is the origin one, that means this is the first, the line drawn, and this is the solvent where the components are separated. Then after some time,
Sir, hello,
yes,
sir.
yes,
This where is the here? Where is the solid liquid phase?
this one,
Solid
this, yes, yes, yes,
mobile solid phase and mobile phase where this one?
yes, the solvent is the mobile phase here, this is the liquid, na, this is the mobile phase, and the
Solid phase, solid
sol
phase.
yes, solid, this paper is the solid phase, TLC,
Yeah,
this is the solid phase here, and this is the mobile phase.
okay.
Two phases are here. So two phases are here. The solvent is the mobile phase, which will move upward through the solid paper, that is TLC plate, and after some time we will see different components get separated by different colorful spots on this plate, and by comparing these spots we can easily trace out which component is present in what amount, or how much extent the reaction is completed. So here another statistical approach is there, that before that we can read out this one, that these spots are generally visualized by using ultraviolet lamps or with the help of hot plate. Okay, by putting the paper or the TLC plate in on the hot plate or UV lamp, under the UV lamp, we can easily see the different spots. Then yes, this is very important, that is the retention factor. The retention factor is from the baseline, this is the baseline. So from the baseline, how much distance this component is traveled in upward direction, and what is the maximum length of the TLC plate. So this is the starting point of the solvent, and this is the maximum height, and it is also highlighted earlier. Okay, so this is the total length which the component can maximum travel, and this is the different distances covered by different components in the mixture. So what is the detention factor? This is the actual distance covered by the component divided by total distance which can be covered, that is will be the retention factor. That means individual distance divided by total distance. So this is be the retention factor, RF. So the value of RF, the value of RF signifies what will be the retention time. So the component which has more affinity towards the solid phase, that is the stationary phase, will travel a few distance, but which has less attraction, it will travel more distance. मतलब जिसका अट्रैक्शन कम हो वो ज्यादा दूर जाएगा और जिसका अट्रैक्शन ज्यादा हो वो कम दूर जाएगा. तो it will travel less because it has more attraction, and it travel more, that means it has less attraction. So this will be the retention factor, that is distance covered by the individual component divided by distance, total distance it can cover. In mathematically it is distance from start to center of the substance spot divided by distance from start to solvent front. And this is paper chromatography. This will be discussed one by one in different units, so I will not go further. This is an example of your paper chromatography. The same thing is there. This is one paper and that is just a plate, thin layer chromatography. This is column chromatography. This is three-dimensional where a column is used. I will taught you in next units. Okay, so let's go to our PDF. So in PDF, we have some general things of your principle. So I already taught these things to you. So what is chromatography, and depending upon your stationary phase, mobile phase, and different processes or mechanisms used for the separation, it will have many types. So classification, that is based on solid support, that is stationary phase, based on mobile phase, and based on the mechanism. So we have two-dimensional chromatography, that is your TLC and paper chromatography, and we have three-dimensional, that is your column chromatography. And here it is very clearly written that in the classification that is based on the mobile phase, there will be three types: liquid, gas, and supercritical fluid. The first two are very well known, but the third one, that is supercritical fluid, is relatively new and doesn't figure so frequently. In spite of some advantages, it has still to become popular. Again, in this type of classification, a large number of chromatography technique with varied mode of separation fall under the head of liquid chromatography. So supercritical fluid chromatography, it is not popularly used till now. So we have different type of chromatography here. Then liquid chromatography is, this is the liquid partition chromatography, where the stationary phase is liquid and solid, stationary phase is liquid and mobile phase is also liquid. So we have different type of that is ascending or descending type chromatography is there. And this type of chromatography is also under your three-dimensional, that is called column chromatography, as well as two-dimensional, okay, where the supporting holding hands are paper and thin layer plates. And we have also the examples like your the examples like your reverse phase in coating is C8 chain, C18 chain, that is octyl decyl type. Just you have to remember these examples. Then we have liquid solid adsorption chromatography is there. This involve in that is your paper chromatography or thin layer chromatography. Then we have ion pair chromatography there, where ion exchange is there. This is another chromatography method is there. We will discuss one by one because you have one unit on these chromatography methods. Paper chromatography is one paper unit, thin layer chromatography is one unit, gas chromatography is there, size exclusion chromatography is there. So one by one we will discuss. Just in this class you just see what are the different type of chromatography and the basic principle we will discuss today. Okay, so here it is written size exclusion chromatography. This is also very useful form of liquid chromatography. This is liquid chromatography employed for the separation of high molecular weight substances. So depending upon the type of substances we wish to separate, different chromatographic methods may be used. So this is also called gel permeation or gel filtration chromatography. Okay, and under these we have cross-linked dextran and polyacrylamide materials are generally used for this chromatographic method. Then we have under gas chromatography we have two types, that is gas solid and gas liquid. So here the first one is the mobile phase and the second one is your stationary phase. So in GSC, that is gas solid chromatography, gas is the mobile phase and solid is the stationary phase, and in GLC we have the gas and liquid type. And also the in different satellites or different astronauts, they used GCMS, that is gas chromatography mass spectroscopy, to detect various unknown things present on different planets or different like your surface of the moon or surface of the Mercury. So different gases, different materials are minutely examined, and the data are coming out, because these are characterized using GCMS, that is gas chromatography mass spectroscopy, where the gas chromatography method is used for the separation and mass spectroscopy is used for the estimation of the mass of that material present in that mixture or the component. So both the activities are done through one instrument, which is known as GCMS, gas chromatography mass spectroscopy. Here it is there, I think. This is HPLC, high performance liquid chromatography, and this is your DCMS. This is LCMS, liquid chromatography mass spectroscopy, and another one is there, that is GCMS under this, I think. And this is GC, just like this. This is LCMS, and this is LCMS. This around I think this is 70 to 80 lakhs, and GCMS is around 1.5 crore. So this is based on your liquid chromatography and mass spectroscopy, and GCMS is more sophisticated than this LCMS, and this will cost more. And supercritical field chromatography, this, yes.
हेलो सर, मैं इकबाल बोल रहा था सर। ये कुछ सर प्रैक्टिकल क्लास प्रोवाइड किए जाएंगे सर?
नो नो, आपका जो प्रैक्टिकल है वो इसके ऊपर नहीं है, क्रोमाटोग्राफी के ऊपर नहीं है। वो आपका जो प्रैक्टिकल है वो
ये एचपीएलसी वगैरह गैस क्रोमेटोग्राफी ऐसे तो प्रैक्टिकली हम लोग को दिखाया तो जाएगा ना सर, या करके सैंपल एनालिसिस करके?
no, these LCMS GCMS are only in research labs in IITs, NITs, your CSIR lab. So these instruments are very costly. The general colleges or university do not able to afford this amount. So that's why these are the theoretical versions you have to read and remember. And in your practical part, you have some water sample analysis, some spectroscopic analysis under your UV visible spectroscopy or IR spectroscopy maximum. NMR is not there, and you have the estimation of that is oxygen, dissolved oxygen, DO, that is COD, BOD. This type of experiments are there. So you have in each paper you have 6 experiments. So just wait. Hello. So so your theory and practical both are different. No relation is there, and you just look out your practical syllabus in IGNOU website. You will have that one. Okay. So supercritical chromatography, this is not needed from your examination point of view, so I will skip this one. And in the conclusion of this first part, we will have some of the classification of chromatography techniques, and it can be said that large number of techniques fall under this category. Head of liquid chromatography, we have liquid chromatography, and then we have gas chromatography is also there, Then we have thin layer chromatography, paper chromatography, size exclusion chromatography, gel permeation chromatography, and supercritical fluid chromatography. This 5 to 6 type of chromatography we have already discussed. Then this is classification on the basis of stationary and mobile phase. So in a liquid chromatography, liquid adsorbed on solid or organic bonded to solid surface. This mechanism is partition type, and these are the mode: column in two-dimensional, normal, reverse phase, this etc. Then we have under this liquid chromatography, we have solid adsorbent, we have again the column, biospecific etc. Ion exchange, we have ion exchange mechanism. Under gas, we have partition, that is column chromatography. We have adsorption, this is also column chromatography. Supercritical fluid chromatography, the mechanism is your partition. Then illusion of the column, how the column is eluted. How the column is eluted? So when the TLC, that is thin layer chromatography or paper chromatography or column chromatography, if it is dipped in the solvent medium, the required solvent medium, then the solvent from the baseline, it will be flow upward, and simultaneously the different components, depending upon their attraction or affinity towards the surface, that is adsorbate, the components gets adsorbed on different dimensions or different distances. So this will be your illusion of the column. Then distances travel versus concentration, this will be drawn by knowing the different datas, that is the retention factor datas. Then we have one component moved at a faster pace and other at a slower rate. These things will be there. This is depending upon their retention factor. The rate of zone broadening for the two species is decreased. These two conclusions are from your plots. Then migration rate, it is related to retention factor again. That is, migration rate means how it is migrated from their baseline. So it is again dependent on the affinity of the component on the adsorbate. If the mechanism is adsorption, that is TLC or paper chromatography. So there is distribution constant is there. That is, if the solute X in mobile phase is equilibrium with solid X in stationary phase, then the distribution coefficient will be concentration in solid phase divided, or stationary phase divided by concentration in mobile phase. This will be the distribution, this will be the equilibrium constant K, and also known as the distribution constant K. So Cs is the concentration of the solute in stationary phase, and Cm is the concentration of the solute in mobile phase. And Cs is directly proportional to Cm over a wide range of concentration. That means when the concentration is very large or wide range of concentration is there, then both the concentration will have the same value, or it is directly proportional. Not same value, it is directly proportional. The chromatography, in such a case, the chromatography is known as a linear chromatography, where the concentration has a wide range. This is known as linear chromatography. Okay. So then retention time is there. So when for a particular time period, two different components travel to different, two different components cover two different distances, on the basis of the distance covered, the retention time can be predicted or calculated. In the preceding subsection, we have introduced the term retention time. It is time taken after sample injection for the analyte peak to reach the detector. So this is your instrumental type, that is your gas chromatography or liquid chromatography. So when you put your sample in the sample chamber, how much time is taken to give the result, it will be the retention time. So similarly, the your equation is there, that is V equal to L by TR, where L is the length of the column. Okay, just I read out this one, where Tm is the time Tm for the on retained species is the same as the average rate of the migration of the mobile phase. L is the length of the column. Average rate of migration of the solute molecule is given by, this is the average rate, V equal to L by length by time. It will be the average. Then average linear rate will be equal to L by Tm. It is the time for the on-retained species, Tm. It is the dead time, that is last time. It is the time required for the average molecule of the mobile phase to pass through the column. After getting familiar with the term distribution constant retention time, we may look into the relation between the two terms, that V equal to U plus U into fraction of the time solute spent in the mobile phase. So just go through these things. These are very simple things, that is just remember, just understood that what is retention factor, what is retention time, what is stationary phase, what is mobile phase, which type of chromatography it is there, what is the mechanism, and how the components are traveled, or components are taking time for their separation. So these are all mathematical expressions, that is V equal to U into moles of the solute mobile phase divided by total mole in the column. So mole means it is concentration into volume is mole, divided by it is concentration is volume, that is mobile phase plus solid phase. That means this is the total, it is total mole, it is individual mole. So individual mole by total mole. So if I go for simplification of this equation, I have the last equation, that is V equal to U into 1 by this much. So retention factor, again the retention factor is individual time taken for a particular component divided by total time, individual distance covered by the one component divided by total distance, So this is in expression, it is Kx equal to Kx Vs by Vm. So if I put V equal to U plus this one, then finally this will come. Okay. Then selectivity factor is there, another factor is there, retention factor, then another factor is selectivity factor. The relative migration rates of the solutes are expressed in terms of selectivity factor. This is relative migration, that is between let us two components gets migrated, then the relative migration means the one retention factor divided by another retention factor. This will be relative migration. So the selectivity factor or separation factor A of a column for two solutes X and Y, that is two components X and Y, then relative or selectivity factor alpha equal to Ky by Kx, where Ky is the distribution constant for Y and Kx is the distribution constant of X. And here also small k is written, this is the retention factor, that is your selectivity factor is also related to your retention factor Ky by Kx. Then shape of peaks, just read out these things, concept of theoretical plates. So in your exam these things will not come, only these different spectroscopic types, different separation methods, these things will come. Concept of theory, these are all research oriented related things are there. Okay, so you need not uh, have to remember all these. There is a research retention time, taken from the injection of sample to the appearance of the peak of the illusion band at the detector. The formula used to calculate n, that is a number of components, like this. Again, there is one rate theory is there. Again, the role of different kinetic variables on zone broadening, the migration of the solute down the column take place as a result of several mass transfer, and there is some time which this mass transfer take place. So when we go for different rates, then generally the liquid chromatography will have high rate with respect to or as compared to the liquid chromatography. This is very logical, that rate in the linear flow rate or linear rate flow in gas will be more than liquid. So these are some basic equations given by Demeter equation, that is H equal to A plus B by U plus Cu. H is the plate height. What is the height of the plate? Let us see if it is thin layer chromatography or paper chromatography, then how much centimeter it is the H has. Generally, we take 5 to 6 centimeter paper chromatography, that is a TLC, thin layer chromatography, for chromatography determination. And this is the linear velocity u in the mobile phase, and ABC are the coefficient related to phenomena of ED diffusion or multiple flow path, longitudinal diffusion, and mass transfer between phases. So these things are there. So these are all constants. Then ED diffusion is there. ED diffusion term A is known as ED diffusion. This factor arises from the multiplicity of pathway for a gas flowing through the column, therefore it is known as multiple flow path. Just see this one. The component is flowing through different path. This is known as multiple flow path, and this it can be determined on the basis of your ED diffusion term, multiple flow path. Okay, the column is packed with particles of various size and shape arranged in an irregular manner. So if the column is packed in irregular manner, then pores will be there with different dimensions, and different components can flow through different paths, or different multiple flow paths will be there. As the carrier gas flow through the channel of packing, it is divided into many streams, some of which may merge and again divided into complex manner. So this is related to your multiple flow path. Then there is a equation, that is A equal to 2 lambda dp, that is A is your ED constant. Lambda is the dimensionless parameter depicting the irregularity of packing, lambda, and dp is the diameter of the particles in centimeter. Longitudinal diffusion term, that is B by U, is there. So A is the ED diffusion. Term is there. B by U is longitudinal, and at last it will be C by U. Okay, which is mass transfer. So longitudinal diffusion of the solute in the gas phase, some of the solute molecules tends to diffuse along concentration gradients. Thus the solute band will broaden as the molecules spread into region of low concentration ahead of the band and behind it. So this is longitudinally the solute concentration will decrease, and it will be broaden as the molecule solute. Okay, the band will broaden. The solute molecules spend part of their time in the gas phase and part in the liquid phase. This type of diffusion is much faster in gas phase than in liquid. So as this broadening is there, that means it will be generally seen or generally faster in gas phase than liquid phase. So generally in GLC, that is gas liquid chromatography, these things are there longitudinal diffusion term, and the term is beta B equal to 2 gamma dm, where B by U equal to 2 gamma dm by U. Okay, so where Y or gamma equal to correction factor, account for irregularity or diffusion pathway through the packing material, and dm is the diffusion coefficient of the solute in the gas phase. And the last term is your Cu, that is mass transfer term, that is not in equilibrium. So this is concentration of L by concentration of G, that concentration of liquid phase divided by concentration in the gaseous phase, which is obeying Henry's law, that is concentration of liquid by concentration of solid in the chromatogram equal to a constant, that is K. So if I multiply these things, this will be concentration of Cl equal to K into concentration of G. And also one extra factor is multiplied, which is known as Ft, and it is function of time, which reflect kinetic of mass transfer process between two phases. That means some mass gets transfer from liquid to gas phase or stationary to mobile phase, and this obey the Henry's law. Then these are some plots are there, that is concentration of G, concentration of L is there. Then what is the type of plot we have seen here. Okay, this is for your ideal distribution. This is non-ideal or actual distribution. This is ideal, that is the gas is in equilibrium with liquid, so the plots are very much same in up and down. But in actual or in a non-ideal state, the distribution is lost just like this. Then go through these things, then Van Demeter plot and zone broadening, the effect of different factor discussed. This is known as Van Demeter plot in 4.9. The carrier gas velocity on the factor affecting the plate height, it is clear that A is not affected. Just read out these things. This is just for your information, and you have to read out all the things. And lastly, the column should be packed with smaller particle to have an uniform flow of different components. The packing should be compact. This is very important. The packing should be compact. That means there must not be any multiple flow rate. The column diameter should be narrow. Column diameter, if the column diameter is narrow, that means the pore size becomes less and less. The thickness of the liquid layer in the column should be minimized. The thickness should be minimized. With gaseous mobile phase, the longitudinal diffusion can be lowered by reducing the temperature. This effect is not noticeable in liquid chromatography because longitudinal diffusion has little effect on the plate height. And lastly, the resolution factor is there. If the foregoing discussion on reducing the broadening of the peak is essential, aim to achieve a minimum overlap between the consecutive peak of the analyte. In other words, the position of the illusion band on the horizontal axis and their width will determine the extent of separation. The quantitative measure of ability of a column to separate two analyte is expressed in terms of resolution factor, that is R. If the this is the resolution factor is there, which is very much important to have the separation, the extent of separation, depending on the illusion, the position of illusion on horizontal axis. This is the horizontal axis, and the width will determine the extent of separation. So the width will determine the extent of separation. So two factors are there, and then this is the equation, that is R equal to delta D. This is the horizontal line. R equal to delta D by Wx2 plus Wy2. These things are there. This is the width, W stands for width, and some factors are multiplied here. Just try to remember these factors. Then we have separation factor. Then at last we have summary. So lastly, This implies that separation will not be achieved, whatever may be the length of the column. If alpha is increases to 1, the number of plates required decreases rapidly. In other words, it is better separation can be achieved by bringing a small change in alpha by changing the liquid rather than bringing a large increase in the length of the column. So in this part, we just gone through different type of chromatography, what is the general principle involved, and what are the scientific factors or scientific principle is involved in this methodology of separation. So in the next class, that is tomorrow, we will discuss unit 5 and 6, and unit 5 is all about your liquid chromatography, LC. Yes, Raut.
यस सर। सर ये बोल रहा था सर, लास्ट का प्रेजेंटेशन था पीपीटी वो शेयर कर देंगे ग्रुप, तो हम लोग के लिए हेल्पफुल रहेगा सर।
नहीं, मैं कर दूंगा। आप नहीं, आपका व्हाट्सएप ग्रुप क्रिएट हो गया क्या?
हाँ सर, व्हाट्सएप ग्रुप क्रिएट है सर। आप अगर फोन नंबर आपका शेयर करेंगे तो हम ऐड कर देंगे सर।
मैं फोन नंबर ये दे रहा हूँ आपको, चैट बॉक्स में मैं लिख दे रहा हूँ, ठीक है?
हाँ सर, लिख
तो
दीजिए सर। और उसमें सर वो यही जो आज का स्लाइड और कल का स्लाइड आपको ये करेंगे तो शेयर कर लेंगे ग्रुप में।
मैं दे दूंगा, कोई बात नहीं। मैं सारा जो पीपीटी में बनाए हूँ वो सारा दे दूंगा आपको, कुछ बात नहीं।
सर हम मिल गया सर, आपका नंबर मिल गया, मैं ऐड कर देता हूँ।
सो ये नंबर ऐड कर दो, मैं पीपीटी जो है शेयर कर लूंगा, ठीक है?
यस सर, थैंक यू।
So in the next unit we will discuss liquid chromatography in unit 5. Then we have planar chromatography, means paper chromatography, and thin layer chromatography in unit 6. So don't be worried that I skip many things, but these things will come again, and we will discuss one by one chromatography in details. So I think if anyone has any doubt or anything wish to share or anything wish to say, so please, the platform is open to you all.
Okay sir, thank you.
Actually, IGNO material is very vast material. So within 1 hour, it is very much difficult to cover all the things. Just I wish to cover the important basic principles or the understandable things to you, and the remaining things which I have skipped, that the mathematical equations or examples, so you may cover all the things. And for examination point of view, the research part is not needed. Okay, yes.
Yes sir, yes, I got it.
Okay.
Hello, sir. My name is Janardhan from Nagpur. Sir,
Yes.
I want to add the WhatsApp group, sir. My number is also WhatsApp group number is.
Actually,
I
IRG, I am not the admin of that group. You may share your
Achha,
number
okay.
in the chat box. Okay. So
Achha.
I think yes, Raut is
Yes,
the
sir.
admin.
Yes sir.
Oh, so I will.
Interested.
Okay. So just wait. I will stay active for 5 minutes in this online platform. So those who are not yet to be added in the WhatsApp group, they may share their WhatsApp number in the chat box, and yes, Raut will add them.
Okay
sir. Sir, one of the small requests, sir. Sir, I want the gas chromatography detail in explanation, sir. If any feature
So
class.
actually, you have one unit related to gas chromatography. So yes,
Okay,
this one. I will teach you in unit 7. Yes, this one.
Okay, sir. Okay.
Actually, today we just cover up the basic principle, different types, different scientific factors related to chromatography. Nothing more. And in your examination, your thin layer chromatography, gas chromatography, and liquid chromatography, these three are very much important, and this might come in your examination. Okay.
Okay, sir. Thank you.
Okay. So yes, Raut, you are instructed to add the numbers posted in the chat box.
Yes, sir. Yes, sir.
So just take the take one photo in your mobile and then add.
Okay, sir. Okay.
So anyone wish to share anything or anything you wish to say? Else I will wind up the session for today, and we will have the next class on 29th, that is on Monday. So
Okay.
tomorrow is the 75th Republic Day of our country. So I wish all a happy Republic Day to you all.
Thank you, sir. Happy
Thank
Republic
you,
Day.
sir. Thank you. Same to you.
Same to you, sir.
Okay. So thank you, students.